In this video, we're going to continue where we left off in class so that we can be all caught up as we continue to transition from one instructor to the next. But we were talking about the power rule, the derivative of a constant function, and the derivative of a linear function. We talked about the constant multiple rule and the derivative of a sum or difference of two functions. And so now that we have all of those rules, now we can actually find the slope of tangent lines, talk about the first derivative at points and the second derivative at points, and now know what they mean, right? And so this example here requests that we find f prime at 3, so the first derivative evaluated at 3, and the second derivative evaluated at 3, right? Given that our function f of x equals x cubed. Well, if I want to do that, right, all I have to do is first find f prime of x, right? So before, what we would have to do is we would use our slope of our secant line over a small interval around 3, right? And I'm just going to use the right-sided slope of the secant line as an estimate, right? Well, we no longer have to do that anymore now that we have our derivative rules, right? And so what we're going to do here is we're going to first find f prime of x. Remember, this is x to a numerical exponent, and so that's the power rule that applies there. And so remember, we bring that 3 out front, and it's now the coefficient, and we reduce that exponent by 1, and so the derivative of x cubed is 3x squared. Well, now that we have our derivative function, if I want to find f prime of 3, then all I have to do is substitute 3 in for x. That's 9 times 3, which is 27, right? And so that's what I get. When I plug in 3 into my derivative function, my output is 27. I can interpret that as, oh, my function is increasing at x equals 3 because the derivative, which is 27, is a positive number. And so we could expect that for a 1 unit increase from 3 to 4 for our x's, our output or our y value should increase by 27. That's a sharp increase. One way that we can interpret that derivative there. Let's go to part B. We want to find f double prime of 3. So this is the second derivative, which is the derivative of the first derivative, right? And so what I can do is I can go here and look at my first derivative, which is 3x squared. And what we're going to do is we're going to take the derivative of that. And so we're doing this for a general x first. And so I'm going to apply my constant multiple because that's 3 times my function x squared. So when I do the derivative, it's still going to have that 3 there because that 3 is understood to be multiplied by the x squared. And then I do the derivative of x squared, which is a power rule. I bring that 2 out front and I reduce that exponent on that x by 1. And so that's 2x. If I simplify that, we end up with 6x. And so now we have our second derivative as a function. We can plug in the specific value requested. And 3 times 6 is 18. And so f double prime of x, f double prime evaluated at 3 is 18. And what this means is my function is concave up at x equals 3, right? Because when the second derivative is a positive number, which 18 is, our function is concave up. This is also telling me, all right, note here, this is also telling me that my first derivative is increasing because its derivative, which is the second derivative, is positive, right? That's some information that we can draw from knowing f double prime of 3 equals 18. The last thing we want to talk about is using the derivative formulas to find the equation of a tangent line, right? Well, before we get there, we are going to let's review some things, right? We want to find an equation, right? When we think of finding an equation, a lot of people like to think of y equals mx plus b, all right? We need to know m, which is our slope of that line, and then we either need to know this b, right? If it's given to us, that's wonderful. If we know our y-intercept or our vertical intercept, that's given to us, then that's perfect. If not, we need a point that the tangent line passes through, right? Now, the slope of your tangent line is equivalent to your derivative at a point, right? And so since the slope of the tangent line to a curve is given by the derivative at the point, we use differentiation to find the equation of the tangent line, right? And it's specifically going to give me the slope of the tangent line, right? Now, we just said that we needed the slope, which we have to find a derivative and plug it in, and that's going to give me the slope of my tangent line. So basically, exactly what we did up here. This 27 here is the slope of the curve at x equals 3, and that's the slope of your tangent line at x equals 3, right? And so if I want to write the equation of my tangent line, I need to find my slope. I'm just going to go through that process, take my derivative and plug in the value where I want my tangent line, right? But what about the actual point, right? Well, what we want to do, and I'm doing this for a general function here. This is not the one that's in the example that's below. But for a general function, I'm just going to do a function that looks maybe something like that, right? And let's say I wanted to know the tangent equation of my tangent line at x equals this value here, x sub 0, right? Well, one thing that's for sure, and we've defined what a tangent line was, is that the point on my curve where we're interested in our tangent line being at, it shares the same ordered pair that our function does at that point, right? So if I know my function, y equals f of x, right? And I know my x value. Well, to get the y coordinate to this point here, all I have to do is substitute my x value into my function, and it's going to spit out my y value, right? And so let's use that in order to help us find our point, right? So again, to find the slope of the tangent line, we find the derivative of the function and plug in the value, right? To find a point that our tangent line passes through, which will allow us to come up with our equation, what we're going to do is we're going to substitute the x value that they give us into our original function so that it can give us the y value, because the point on the tangent line is exactly the same point on the curve, right? And so let's do that. So first, let's find our slope. All right, well, we got to find f prime of x. Our derivative here, our power rule, that would be a 2x to the first power. And the derivative of 2, that's a constant, that's 0, right? And so f prime of x equals 2x. Now, our goal is to find the equation of the tangent line at x equals 1. So we need the slope at x equals 1. That means we're going to substitute 1 in for x. We get a slope equal to 2, right? We also need a point that our line passes through. Well, I know that f of x equals x squared plus 2. I know I have an x value of 1. When I plug in 1 into that function, I'm going to get an output that is the y coordinate to that function, which is 3. And so our point here is going to be the point, not 0, but it's going to be the point 1, 3. All right? Plug in 1 into your function, you get an output of 3. And so my equation of tangent line, if I use y equals mx plus b, I'm going to substitute 2 in for my m. My x coordinate is 1 to a point that line passes through. My y coordinate is 3. We get 3 equals 2 plus b. Subtract 2 from both sides, b equals 1. And so my equation of my tangent line, y equals 2x plus 1. So what we're going to do here is we're going to determine if this is actually correct. And so what I'm going to do is go to part B, and I'm going to graph both of these functions together, right? So let's turn on our calculator. We're going to go to y equals, and y equals x squared plus 2. And then I have the line 2x plus 1. Press enter. And then I'm going to go to zoom 6 to get my normal viewing window. And as we can see, we have a tangent line that's going to touch my graph specifically at the point where x equals 1, and it's going to be at the point 1, 3. All right, and there we go. We've found the equation of the tangent line. We find a derivative, plug in the x value, that'll give us our slope. And the point we need to come up with our equation of our tangent line, we go back to the original function, plug in our x value so that we can get the associated y value. That concludes this video. Have a good one.